Welcome to Sleepy Parallax. We're going to tell the entire story of the Big Bang, from the first incomprehensible fraction of a second to the vast universe we see today, billions of years later. Don't worry if you drift off along the way. In fact, that's rather the point. This story spans 14 billion years after all. There's no rush. Let time unfold gently, naturally, the way it did in those first moments when time itself was being born. So settle in, adjust your pillow, take a slow breath. And let's begin at the beginning, or rather, at the moment just before there was a beginning at all. Here's a question that has no answer, but we'll ask it anyway. What was there before the Big Bang? Before time, before space, before matter and energy and light and darkness? Before anything at all? The honest answer is we simply don't know. More than that, the question itself might not even make sense. You see, the word before requires time. It needs a past and a present, a then and a now. But if time itself began with the Big Bang, then asking what came before is a bit like asking what's north of the North Pole. The question falls apart under its own weight. There is no north of the North Pole. North ends there. Similarly, there may be no before the Big Bang. Time itself might have started then. This is hard for our minds to grasp. We're so used to time flowing, always flowing, like a river with no beginning and no end. We wake up, the day unfolds, night falls, we sleep, and then tomorrow arrives. Time, for us, is the most reliable thing in existence. But physics tells us something different. Time, according to Einstein's theory of relativity, isn't absolute. It's woven together with space into something called space-time. And space-time itself can bend, stretch, and warp. At the moment of the Big Bang, space-time itself came into being. So asking what happened before that is like trying to find a frame of a movie that exists before the film begins. There is no frame zero. The first frame is the first frame. But still, we wonder. Humans are built to wonder. Some theories suggest that perhaps our universe emerged from something called a quantum fluctuation, a random blip in a field of energy that exists outside of space-time as we know it. Others propose that our universe might be one of many, a bubble in an infinite foam of universes, each with its own laws of physics, its own story. These ideas exist at the very edge of science, where mathematics meets philosophy, where equations trail off into the unknowable. What we can say with some confidence is this. About 13.8 billion years ago, give or take a few tens of millions of years, something extraordinary happened. The universe, as we know it, began, not from nothing exactly, because even nothing is something when you think about it. The universe began from a state so extreme, so compressed, so unimaginably hot and dense that our normal laws of physics simply break down. Imagine trying to compress everything, and I mean everything, all the matter and energy that would eventually become stars and galaxies and planets and people. Imagine compressing all of that into a space smaller than the period at the end of this sentence. Actually, smaller than an atom, smaller than the nucleus of an atom, smaller than anything we have words for. This wasn't an explosion in space. This was an explosion of space. Space itself was born in that moment, and it began expanding, carrying everything with it. There was no center to this expansion. It wasn't like a bomb going off with a specific point of origin that you could point to and say, there, that's where it happened. Every point in the universe was the center. Every point in the universe is still the center, in a sense, because space itself is what's expanding, not objects moving through space. This is one of the most beautiful and confusing aspects of the Big Bang. Galaxies aren't flying apart through empty space like shrapnel from an explosion. Space itself is growing, and galaxies are being carried along like raisins in rising bread dough. As the dough expands, the raisins move apart from each other, not because they're moving through the dough, but because the dough itself is growing. So we find ourselves here at the threshold, about to step into a story that begins with no before, in a place that is no place, at a time that is the very first moment of time. It's dizzying, it's profound, it's the kind of thing that makes you feel very small and very connected all at once. Let's begin. The Planck epoch. Even the name sounds mysterious, doesn't it? This is the very first chapter of our story, the opening line of the cosmic narrative. It lasted from time 0, the actual moment of the Big Bang, to about 10 to the negative 43 seconds later. That's a decimal point followed by 42 zeros and then a 1. It's such a tiny sliver of time that it barely deserves to be called time at all. To put this in perspective, more time passes between 2 ticks of a clock than all of the Planck epoch combined, repeated billions upon billions upon billions of times. It's the shortest meaningful unit of time that physics can describe, named after Max Planck, the father of quantum mechanics, who first calculated this fundamental timescale. During this first instant, the universe was unimaginably small and unimaginably hot. We're talking about temperatures around 10 to the 32 degrees Kelvin. That's 100 million degrees. Numbers this large stop having meaning in any practical sense. They become pure abstraction, mathematical poetry describing something that defies all experience. At this temperature, at this density, everything we know about physics simply stops working. The 4 fundamental forces of nature, gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, these weren't separate yet. They were unified into a single superforce, a kind of cosmic oneness where all the rules we use to understand the universe today were merged into something we don't yet fully understand. This is where quantum mechanics and general relativity, the 2 great pillars of modern physics, come crashing together, and neither one knows quite what to do. Quantum mechanics describes the very small, the world of atoms and particles. General relativity describes gravity and the very large, the bending of space-time by mass and energy. Both theories are spectacularly successful in their own domains. But at the Planck scale, during the Planck epoch, both of them are needed simultaneously, and they don't play well together. This is the realm of quantum gravity, a theory we don't yet have, despite decades of brilliant minds working on the problem. String theory, loop quantum gravity, and other approaches are all attempts to bridge this gap, to find a unified theory that can describe the Planck epoch in detail, but for now it remains tantalizingly out of reach. What we can say is this. During the Planck epoch, the universe was a seething foam of energy, fluctuating wildly, with space-time itself vibrating and churning at the smallest possible scales. Particles, if we can even call them that, blinked in and out of existence. Cause and effect, past and future, these concepts as we understand them might not have applied in any normal sense. Some physicists describe the Planck epoch as a kind of fuzzy boundary to the universe, a quantum fog where space-time becomes granular rather than smooth, made up of tiny discrete units like pixels on a screen. Others suggest that time itself might have been imaginary during this period, a mathematical dimension that only became real as the universe cooled and expanded. The truth is, we're reaching the limits of what we can know, and that's okay. There's something humbling and beautiful about standing at the edge of knowledge and peering into the mist beyond. It reminds us that science isn't about having all the answers. It's about asking better and better questions. As the universe expanded and we're still in the first fraction of a second here, remember, it cooled ever so slightly. The temperature dropped from utterly impossible to merely unimaginable, and as it cooled, something remarkable happened. The first symmetry breaking occurred. Gravity, the weakest of the 4 forces but the one that shapes the cosmos on the largest scales, separated from the other 3 forces. This marks the end of the Planck epoch and the beginning of what's called the Grand Unification epoch. The universe was about to undergo a series of transitions, each one defining new rules, new possibilities, new chapters in the story of existence. But before we move forward, let's pause for just a moment. Let's sit with this. Everything you see, every star in the night sky, every atom in your body, every thought you've ever had, all of it traces back to this moment, to this incomprehensibly hot, incomprehensibly dense point of pure energy at the very beginning of time. You are made of star stuff, as Carl Sagan famously said. But even more than that, you are made of Big Bang stuff. The atoms that form your cells were forged in the first few minutes of the universe's existence, and then scattered across space by dying stars. You are literally a way for the universe to know itself, a small piece of that original unified energy, now conscious, now aware, now wondering about its own origins. There's something deeply moving about that. We'll return to this thought later, but for now, let's continue forward through time. The grand unification epoch began when gravity split off from the other forces, around 10 to the negative 43 seconds after the Big Bang. It lasted until about 10 to the negative 36 seconds, which sounds like a trivially short time, and it is, but it's roughly 1 billion times longer than the Planck epoch, which in the context of these early moments counts as quite leisurely. During this period, the temperature of the universe had dropped to about 10 to the 27 degrees Kelvin. Still outrageously hot, still a realm where nothing like matter as we know it could exist, but cool enough that physics as we understand it starts to have something meaningful to say. Three forces remained unified: electromagnetism, the weak nuclear force, and the strong nuclear force. Together they formed what physicists call the electronuclear force, or the grand unified force. Gravity was now separate, off doing its own thing, gently trying to pull the universe back together even as expansion pushed it apart. The mathematics describing this grand unification is elegant and beautiful, even if we can't fully test it experimentally. The equations suggest that at these energies, particles that we think of as completely different, electrons and quarks for instance, were actually interchangeable aspects of the same underlying thing. It's similar to how ice, water and steam are all H2O, just in different states depending on temperature. If we could have witnessed the universe during this epoch, we would have seen, well, nothing, actually. There was no light to see by, and even if there was nothing resembling an eye or a sensor that could detect it. But if we could somehow perceive what was happening, we would see a roiling chaos of energy, with particles and antiparticles materializing and annihilating in a cosmic dance. And then, around 10 to the negative 36 seconds after the Big Bang, something absolutely extraordinary happened. Something that would shape the entire future of the cosmos. The strong nuclear force separated from the electroweak force, which itself would later split into electromagnetism and the weak force. But this separation, this symmetry breaking, released an enormous amount of energy, and this energy drove what might be the most dramatic event in the history of the universe. Cosmic inflation. Cosmic inflation. The name almost undersells it. This wasn't a gentle expansion. This was an explosive, exponential, mind-bending growth of space itself that dwarfs anything we can imagine. In a period lasting from about 10 to the negative 36 seconds to 10 to the negative 32 seconds, the universe expanded by a factor of at least 10 to the 26th power. Let that sink in for a moment. The universe doubled in size, then doubled again, and again, and again, at least 86 times in a row, all happening faster than you can blink. Actually, much faster than you can blink. Much faster than light can cross the nucleus of an atom. In this brief instant, the observable universe grew from something smaller than a proton to something about the size of a grapefruit or perhaps even a beach ball, depending on the details of the inflationary model. To put this in perspective, if you started with something the size of a grain of sand and expanded it by this same factor, you'd end up with something larger than the observable universe is today. It's expansion on a scale that seems absurd, impossible, more like science fiction than science, and yet the evidence for inflation is remarkably strong. Why did this happen? The best explanation we have involves something called the inflaton field, a hypothetical energy field that filled all of space. Think of it as being in a false vacuum state, a kind of temporary high-energy configuration, like a ball balanced on the top of a hill. The ball wants to roll down to the valley below where it's more stable, but for a brief moment it's stuck up there, full of potential energy. When the strong force separated, the inflaton field suddenly found itself in this unstable state. And as it began to decay to a lower energy state, the energy it released didn't heat the universe directly. Instead, it drove space itself to expand exponentially. The expansion fed on itself, becoming faster and faster, each tiny fraction of a second doubling the size of the universe. This solves several puzzles that had troubled cosmologists. One is called the horizon problem. When we look at the cosmic microwave background radiation, the afterglow of the Big Bang that we can still detect today, we see that it's incredibly uniform. The temperature is the same in all directions to within about 1 part in 100,000. But without inflation, different parts of the universe would never have been in contact with each other, never had a chance to even out their temperatures. How could they be so similar? Inflation solves this by saying that before inflation, the entire observable universe was indeed small enough that all parts of it were in contact, could exchange energy, could reach equilibrium. Then inflation stretched that tiny equilibrated region into something enormous, maintaining that uniformity across vast distances that could no longer communicate. Inflation also explains why the universe is so flat. The geometry of space can be curved like the surface of a sphere, or saddle-shaped, or flat like a sheet of paper. Measurements tell us that our universe is very, very flat on large scales. Without inflation, this would be an incredible coincidence, requiring the initial conditions of the Big Bang to be fine-tuned to impossible precision. But inflation automatically flattens any initial curvature, the way blowing up a balloon stretches out wrinkles in its surface. Perhaps most beautifully, inflation explains where the seeds of large-scale structure came from. Before inflation, the universe was subject to quantum fluctuations, tiny random jitters in the energy and density of space. These fluctuations were microscopic, utterly insignificant, but inflation took these quantum jitters and stretched them to cosmic sizes. The slightly denser regions would eventually, over hundreds of millions of years, attract more matter through gravity and become the cores of galaxies and clusters of galaxies. The slightly less dense regions would become the voids we see in the large-scale structure of the universe today. In other words, the arrangement of galaxies across billions of light-years, the cosmic web of filaments and voids, traces its origin to quantum uncertainty in a region of space smaller than an atom. It's one of the most profound connections in all of science, linking the smaller scales to the largest, the quantum realm to the cosmic arena. When inflation ended, around 10 to the negative 32 seconds after the Big Bang, the inflaton field finished decaying. Its energy was converted into a hot soup of particles reheating the universe. The exponential expansion stopped, replaced by the more sedate expansion driven by normal matter and energy and radiation. The universe was still expanding, still cooling, but at a much more reasonable pace now. And the universe was also much, much larger. A region that had been smaller than a subatomic particle was now something like 10 centimeters across, roughly the size of a grapefruit. Everything that would become our observable universe, everything we can ever see or detect, all 100 billion galaxies with their 100 billion stars each, all of that came from this grapefruit-sized patch of space. Outside this region? We don't know. The universe beyond our horizon is forever beyond our reach. Its light will never have time to get to us, because space itself is expanding too quickly. There could be infinite space out there, an endless ocean of cosmos, but we're confined to our local bubble, our grapefruit-sized seed that grew into everything we know. Inflation remains one of the most successful ideas in cosmology, explaining multiple independent observations with one elegant mechanism, and yet we still don't fully understand it. We don't know exactly what the inflaton field was, or what triggered inflation to start and stop, or whether there might have been multiple periods of inflation. These are active areas of research, with physicists developing more and more sophisticated models and searching for subtle imprints that inflation might have left in the cosmic microwave background or in the distribution of matter. What we do know is that inflation fundamentally shaped the universe we inhabit. Without it, the cosmos would look very different, perhaps so different that galaxies, stars, planets, and life might never have formed at all. In a very real sense, we owe our existence to this brief moment of exponential expansion in the first trillionth of a trillionth of a trillionth of a second of cosmic history. It's enough to make your mind spin. So let's take a breath. Let's let these ideas settle for a moment. The universe has now grown from nothing to something the size of a grapefruit in less time than it takes for light to cross the width of an atom, and we're still in the first second of existence. The journey is just beginning. As inflation ended and the universe reheated, we enter what's called the electroweak epoch, lasting from about 10 to the negative 32 seconds to 10 to the negative 12 seconds after the Big Bang. During this time, the universe continued expanding and cooling, but now at a pace that seems almost leisurely compared to the wild ride of inflation. The temperature was still about 10 to the 15 degrees Kelvin at the start of this epoch, unimaginably hot, but cool enough that fundamental particles could start to exist in forms we might recognize if we had a powerful enough particle accelerator. This is the realm that the Large Hadron Collider at CERN tries to recreate, smashing particles together at enormous energies to see what happens when you approach the conditions of the early universe. During the electroweak epoch, three forces remained: gravity, the strong nuclear force, and the electroweak force. That last one, the electroweak force, was a unified combination of electromagnetism and the weak nuclear force. In our low-energy universe today, these behave very differently. Electromagnetism gives us light, electricity, magnetism, and holds atoms together. The weak nuclear force causes radioactive decay and powers the fusion reactions in the sun. But at high enough energies, they merge into a single interaction. Experiments at particle accelerators have confirmed this electro-weak unification, which gives us confidence that our understanding of this epoch is on the right track. The universe was filled with a seething plasma of fundamental particles: quarks, electrons, neutrinos, photons, and their antiparticles, all colliding and transforming into each other in a chaotic dance. Then, at about 10 to the negative 12 seconds after the Big Bang, the temperature dropped below about 10 to the 15 degrees Kelvin, and the electroweak force split into electromagnetism and the weak force. All four fundamental forces were now separate and distinct. The universe had settled into the rules of physics that govern it today. This marked the beginning of the quark epoch, and this is where things get particularly interesting from the perspective of matter. You see, up until now, the universe was too hot for anything resembling matter to exist. But as the temperature continued to drop, conditions became just right for quarks to play their starring role. Quarks are the building blocks of protons and neutrons, which in turn are the building blocks of atomic nuclei. There are 6 types of quarks with whimsical names: up, down, charm, strange, top, and bottom. The lightest ones, up and down quarks, are what make up ordinary matter. A proton consists of 2 up quarks and 1 down quark bound together. A neutron consists of 1 up quark and 2 down quarks. But quarks don't exist in isolation. They're always bound together by the strong nuclear force, carried by particles called gluons. And here's the quirky thing about quarks and gluons. The more you try to pull them apart, the stronger the force between them becomes. It's like trying to separate the north and south poles of a magnet by cutting it in half. You just end up with 2 smaller magnets, each with its own north and south pole. Similarly, if you pump enough energy into trying to separate quarks, you create new quark-antiquark pairs rather than freeing the original quarks. During the quark epoch, from about 10 to the negative 12 seconds to 10 to the negative 6 seconds after the Big Bang, the universe was filled with what physicists call a quark-gluon plasma. This is a state of matter so hot and dense that quarks and gluons weren't bound into protons and neutrons yet. They roamed freely, crashing into each other, annihilating with their antiparticles in bursts of energy, then reforming. This quark-gluon plasma has been recreated for fleeting instants in particle colliders by smashing heavy nuclei together at close to the speed of light. The conditions achieved in these experiments for just microseconds mirror what the entire universe was like during the quark epoch. It's one of the most remarkable achievements of modern physics, recreating in a laboratory the conditions that existed in the first microsecond of cosmic history. The universe during this time was unimaginably violent and chaotic. Particles and antiparticles were constantly being created and destroyed. For every quark there was very nearly an antiquark. For every electron, a positron. Matter and antimatter in almost equal proportions locked in mutual annihilation And here we come to one of the great mysteries of cosmology. Why do we exist at all? You see, if matter and antimatter had been created in exactly equal amounts, they should have completely annihilated each other as the universe cooled, leaving nothing but radiation. No matter, no atoms, no stars, planets, or people. Just an empty universe filled with light. But clearly that's not what happened. We're here. Stars are here. Galaxies are here. There's matter all around us, and almost no antimatter. Somehow, in those early moments, there was a tiny asymmetry, an imbalance. For every billion antiquarks, there were 1,000,000,001 quarks. For every billion positrons, 1,000,000,001 electrons. This 1 in a billion excess of matter over antimatter is the reason anything exists. When the matter and antimatter annihilated each other, that tiny leftover fraction survived. And that leftover fraction is everything. All the matter in all the galaxies in the entire observable universe comes from that slight imbalance in the first microsecond of cosmic history. Why was there this asymmetry? We don't fully know. It's called baryogenesis, the creation of baryons, which is the category that includes protons and neutrons. There are theoretical models involving subtle differences in how matter and antimatter behave under certain conditions, related to something called CP violation in particle physics. Experiments have detected hints of these differences, but the story isn't complete yet. What we do know is that whatever caused this asymmetry, whether it was a quirk of particle physics, or a consequence of the conditions during inflation, or something else entirely, it was crucial. Without it, we wouldn't be here to wonder about it. As the quark epoch continued and the universe kept expanding and cooling, we reached about 10 to the negative 6 seconds after the Big Bang. The temperature had dropped to about 10 to the 13 degrees Kelvin, which was cool enough for a major transition. Quarks began binding together to form hadrons. Hadrons are composite particles made of quarks. The most familiar hadrons are protons and neutrons, collectively called baryons. This moment, when quarks condensed out of the plasma and formed protons and neutrons, is called hadronization, or the quark-hadron transition. It's similar to how water vapor condenses into droplets when it cools, except instead of molecules clumping together, fundamental particles were binding into composite ones. The hadron epoch had begun, lasting from about 10 to the negative 6 seconds to 1 second after the Big Bang. The universe was now filled with protons, neutrons, electrons, neutrinos, photons, and a small amount of dark matter, all swimming in a hot, dense soup. The temperature was still about 10 billion degrees Kelvin at the start, gradually cooling to about 1 billion degrees by the end. During this time, particles were constantly colliding. Protons could temporarily merge with electrons to form neutrons and neutrinos. Neutrons could decay back into protons, electrons, and antineutrinos. A dynamic equilibrium existed with particles converting back and forth. But as the universe continued to cool, this equilibrium began to shift. Neutrons are slightly heavier than protons, so forming a neutron requires a bit more energy than forming a proton. As temperatures dropped, it became harder and harder to create neutrons. By the end of the Hadron epoch, about 1 second after the Big Bang, the ratio of neutrons to protons had frozen in at about 1 neutron for every 7 protons. This ratio would turn out to be incredibly important, because it would determine the composition of the universe for billions of years to come. But before we get to that, there was one more transition to go through. Around 1 second after the Big Bang, the temperature had cooled to about 10 billion degrees Kelvin. This is still hot enough to vaporize anything made of atoms instantly, but it was cool enough that neutrinos, those elusive particles that barely interact with anything, stopped colliding with other particles frequently enough to stay in equilibrium. Neutrinos decoupled from the rest of matter and radiation. They began free streaming through the universe, and they've been streaming ever since. There's a cosmic neutrino background, similar to the cosmic microwave background but much harder to detect, that dates from this moment. The universe is bathed in these ancient neutrinos, trillions of them passing through your body every second, ghosts from the first second of creation. The lepton epoch, named after the class of particles that includes electrons and neutrinos, continued until about 10 seconds after the Big Bang. By this point, The temperature had dropped to about 1 billion degrees Kelvin. The universe was still far too hot for atoms to form, but it was cool enough that something remarkable was about to happen. The universe was about to start cooking. We are now about 3 minutes into the life of the universe. 3 minutes. Less time than it takes to soft-boil an egg, and yet we've already travelled through epochs of physics that required centuries of human effort to understand even partially. The temperature has dropped to about 1 billion degrees Kelvin. To give you a sense of scale, the core of our Sun is about 15 million degrees Kelvin, so the entire universe at this point was about 70 times hotter than the centre of the Sun. Still extraordinarily hot, but cool enough for something extraordinary to begin, the formation of atomic nuclei. This period, from about 3 minutes to 20 minutes after the Big Bang, is called Big Bang nucleosynthesis, or primordial nucleosynthesis. It's one of the key pieces of evidence supporting the Big Bang theory, and it's a beautiful example of how physics can make precise predictions about events that happened billions of years ago. Let's set the scene. The universe is filled with protons, neutrons, electrons, photons, and neutrinos, all still in a hot plasma. Remember that ratio of neutrons to protons that had frozen in at about 1 to 7? That's going to matter now. Free neutrons are unstable. Left alone, a neutron will decay into a proton, an electron, and an antineutrino with a half-life of about 10 minutes. But in the hot conditions of the early universe, neutrons could bind together with protons before they had a chance to decay. And once bound into a nucleus, they become stable. The first step in nucleosynthesis is the formation of deuterium, also called heavy hydrogen. Deuterium is a nucleus with 1 proton and 1 neutron. In our universe today, deuterium is relatively rare, but in those first few minutes as protons and neutrons collided, deuterium began to form in abundance. However, there was a bottleneck. As soon as deuterium formed, it was immediately blasted apart again by the intense radiation filling the universe. Photons had enough energy to break deuterium nuclei back into free protons and neutrons. Only when the universe cooled below a certain threshold temperature, around 900 million degrees Kelvin, could deuterium start to accumulate without being instantly destroyed. This threshold was reached about 3 minutes after the Big Bang, and then nuclear synthesis could really get going. Deuterium nuclei began capturing additional neutrons to form tritium, an isotope of hydrogen with 1 proton and 2 neutrons. Alternatively, deuterium could capture a proton to form helium-3, which has 2 protons and 1 neutron. Then came the main event, the formation of helium-4, the most common isotope of helium with 2 protons and 2 neutrons. Helium-4 is incredibly stable, much more so than tritium or helium-3. Once formed, it wasn't going to break apart again. And because the universe started with 1 neutron for every 7 protons, and because nearly all available neutrons ended up in helium-4 nuclei, the math works out to a very specific prediction. About 25% of the mass of ordinary matter in the universe should be helium-4, with the remaining 75% being hydrogen. There should also be trace amounts of deuterium, helium-3, and lithium-7, another stable nucleus that formed in small quantities during this period. And here's the beautiful thing. When we look at the universe today, measuring the abundances of these light elements in the oldest stars and gas clouds we can find, what do we observe? About 25% helium by mass, 75% hydrogen, and trace amounts of deuterium, helium-3 and lithium-7 in almost exactly the proportions predicted by Big Bang nucleosynthesis. This agreement between prediction and observation, spanning about 14 billion years, is one of the great triumphs of modern cosmology. It's not just that the theory predicts these numbers, it's that it predicts them with remarkable precision. And those predictions have held up under decades of increasingly accurate measurements. This is evidence that doesn't rely on complex instruments or indirect observations. It's written into the very composition of matter throughout the universe. Every helium atom in existence, whether it's in a distant star or floating in the atmosphere of Jupiter or inside a party balloon, most of that helium was created in these first 20 minutes of cosmic history. There's something profound about holding a helium balloon and realizing that the atoms inside are older than Earth, older than the Sun, older than our galaxy. They're primordial, forged in the crucible of the Big Bang itself, when the entire universe was a stellar furnace. By about 20 minutes after the Big Bang, nucleosynthesis was essentially over. The universe had cooled below about 100 million degrees Kelvin, too cool for nuclear fusion to continue. The neutrons that hadn't been incorporated into nuclei had decayed into protons. The cosmic recipe was set: 3/4 hydrogen, 1/4 helium, and a sprinkling of other light elements. But these were just nuclei, bare atomic cores without electrons. The universe was still far too hot for electrons to settle down into orbit around these nuclei to form neutral atoms. That wouldn't happen for another several 100,000 years. For now, the electrons remained free, zipping through space, colliding with photons, keeping the universe opaque like a thick fog. And so we enter what's called the photon epoch, though it overlaps with what we've already described. This is the period when the energy density of the universe was dominated by radiation rather than matter. Photons outnumbered matter particles, and they carried most of the energy. The universe at this stage was something like the interior of a star, but spread across all of space. It glowed with intense radiation, a blinding furnace of light. If you could somehow exist in this universe, which of course you couldn't, you wouldn't be able to see anything because light couldn't travel freely. Photons would scatter off free electrons after travelling only a tiny distance, bouncing around in a cosmic pinball game. As the universe continued expanding, it continued cooling, following a simple rule. As space doubles in size, the temperature drops by half. The expansion was slowing down gradually under the pull of gravity, but it was still carrying galaxies to be apart, still stretching wavelengths of light, still moving inexorably forward through time. And for hundreds of thousands of years, not much changed. The universe expanded, cooled, remained a hot plasma. Stars hadn't formed yet. Galaxies hadn't formed. There was nothing to see, nothing to mark the passage of time except the slow, steady cooling. This was a patient universe, taking its time, letting physics work at its own pace. But change was coming. Slowly, gradually, inevitably, the universe was approaching a moment that would transform everything. The moment when light itself would be set free. We've now reached about 380,000 years after the Big Bang. In cosmic terms, this is still very early, but compared to those first frantic seconds, we're now in an era of relative calm. The universe has been expanding and cooling steadily. The temperature has dropped to about 3,000 degrees Kelvin, roughly half the temperature of the surface of the Sun. This temperature is significant. It represents a threshold. Below this temperature, something remarkable happens. Electrons can finally settle into orbit around atomic nuclei without immediately being knocked loose by energetic photons. Atoms, neutral atoms, can finally form and remain stable. This transition is called recombination, though that's a bit of a misnomer because the electrons and nuclei weren't combined before, so they're not really recombining. They're combining for the first time. But the name has stuck in the scientific literature, so recombination it is. As the temperature dropped through this critical threshold, electrons throughout the universe began binding to hydrogen and helium nuclei. Protons captured electrons to become neutral hydrogen atoms. Helium nuclei captured 2 electrons to become neutral helium atoms. Over a relatively short period, cosmically speaking, perhaps tens of thousands of years, the universe transformed from an opaque plasma into a transparent gas. This change was dramatic. Before recombination, photons couldn't travel far without scattering off free electrons. The universe was like a thick fog, impossible to see through. But once electrons were bound into atoms, photons suddenly had clear sailing. There were no longer free electrons to scatter off of, so light could travel unimpeded across space. The universe became transparent for the first time. Light was set free. These photons that were released when the universe became transparent, they're still around today. They've been travelling through space for nearly 14 billion years, cooling as the universe expands, their wavelengths stretched from visible light to microwaves. We detect them as the cosmic microwave background radiation, or CMB, a faint glow that comes from every direction in space with a nearly uniform temperature of about 2.725 degrees Kelvin, just a few degrees above absolute zero. The discovery of the cosmic microwave background in 1965 by Arno Penzias and Robert Wilson, quite by accident while they were trying to eliminate noise from a radio antenna, was one of the most important confirmations of the Big Bang theory. They'd stumbled upon the afterglow of creation itself, and it earned them the Nobel Prize in Physics. The CMB is the oldest light in the universe. When we map it across the sky, we're seeing a snapshot of the universe as it was 380,000 years after the Big Bang. We're looking back in time, seeing the pattern of slight temperature variations, tiny differences of about 1 part in 100,000, that correspond to slight differences in density. These density variations, remember, have their origin in quantum fluctuations during inflation, stretched to cosmic scales. The slightly denser regions show up as slightly warmer spots in the CMB, and the slightly less dense regions as cooler spots. These tiny ripples in the fabric of the early universe were the seeds that would eventually grow into galaxies, clusters, and the vast cosmic web of structure we see today. Satellites like COBE, WMAP, and Planck have mapped the cosmic microwave background with exquisite precision, giving us baby pictures of the universe, showing us what it looked like in its infancy. The patterns we see encode information about the geometry of space, the composition of the universe, the rate of expansion, and countless other cosmic parameters. The CMB is a treasure trove of information, a Rosetta Stone for cosmology. But after recombination, after the universe became transparent, something interesting happened. Or rather, something interesting stopped happening. Without free electrons to interact with, and without stars yet formed to generate new light, the universe entered a period called the Cosmic Dark Ages. This is one of the most mysterious and least understood periods in cosmic history, lasting from about 380,000 years after the Big Bang to somewhere around 150 to 200 million years later, when the first stars began to form. During the Dark Ages, the universe was dark in a way it has never been since and will never be again. There were no stars, no galaxies, no quasars, no supernovae. Just darkness, filled with neutral hydrogen and helium gas, slowly being pulled together by gravity into ever denser clumps. It wasn't completely dark in the sense of being empty. The cosmic microwave background still filled space, though it was cooling rapidly and shifting from the visible spectrum into the infrared and eventually microwave range. But there was no visible light being generated. If you could somehow be transported to this era, floating in the vast emptiness, you would see nothing. Perfect, complete darkness in every direction. And yet, beneath this darkness, the future was taking shape. Gravity was working quietly, patiently, pulling matter together. The slight density enhancements that had been imprinted during inflation and amplified over time were now becoming gravitationally significant. Dark matter, which doesn't interact with light or normal matter except through gravity, was clustering first, forming invisible halos. Dark matter is one of the great mysteries of modern physics. We know it exists because we can see its gravitational effects on galaxies and galaxy clusters. There's far more dark matter in the universe than ordinary matter, about 5 times as much by mass. And during these dark ages, dark matter was already hard at work, creating the gravitational scaffolding that ordinary matter would eventually fall into. The ordinary matter, hydrogen and helium gas, began flowing into these dark matter halos, piling up, getting denser and denser. In the densest regions, gas clouds were collapsing under their own weight, compressing, heating up slightly from the gravitational energy being converted to thermal energy. The universe was preparing for its next great transformation. Somewhere, in the depths of the Dark Ages, in the heart of a collapsing gas cloud enriched by dark matter, the conditions were becoming just right for ignition. The universe was about to light up again, but it would take time. Hundreds of millions of years of slow, patient collapse, of matter gathering together, of density increasing atom by atom. The Dark Ages were a period of waiting, of potential building, of the stage being set for the most magnificent show in cosmic history. The birth of the first stars. Imagine the universe about 200 million years after the Big Bang. It's still incredibly young, still dark, still filled mostly with neutral hydrogen and helium drifting through space. But in certain places, in regions where dark matter has concentrated most densely, something is stirring. Gas clouds are collapsing, slowly at first, then faster as gravity strengthens. These clouds are enormous, containing thousands or even hundreds of thousands of times the mass of our Sun. As they collapse, they heat up following the same principle that makes a bicycle pump warm when you compress air inside it. Gravitational potential energy is converting into thermal energy, kinetic energy, the energy of atoms moving faster and faster. At the core of these collapsing clouds, temperatures are rising. 10,000 degrees Kelvin, 100,000 degrees, 1 million degrees. Densities are increasing too, with more and more atoms packed into smaller and smaller spaces. The gas is becoming opaque again as atoms collide frequently, and pressure begins to build, resisting the collapse. But gravity is relentless. It keeps squeezing, keeps compressing, keeps heating the core, and then, somewhere around 10 million degrees Kelvin, something extraordinary happens. The atomic nuclei in the core are moving so fast, colliding so violently, that they overcome the electromagnetic repulsion between their positive charges. They fuse together. Hydrogen nuclei, single protons, smash into each other and stick, forming deuterium. The deuterium captures another proton to become helium-3. Two helium-3 nuclei collide and form helium-4, releasing 2 protons in the process. This is the proton-proton chain, the same nuclear fusion process that powers our Sun and most stars today. And with fusion comes energy. Enormous amounts of energy. When nuclei fuse, they convert a tiny fraction of their mass into energy. According to Einstein's famous equation, E equals mc squared. That's c, the speed of light, is a very large number, and when you square it, it becomes enormous. So even converting a tiny amount of mass releases tremendous energy. This energy floods outward from the core of the collapsing cloud, generating intense radiation pressure that pushes back against gravity. The collapse stops. An equilibrium is reached, with gravity trying to compress the star and radiation pressure pushing outward. The two forces balanced in a cosmic tug-of-war. A star is born. Actually, millions and millions of stars are being born, scattered across the universe in different regions where gas has collapsed. These first stars, called population 3 stars, or sometimes simply the first stars, were different from stars today in important ways. They were enormous, much larger than typical stars in our modern universe. Estimates suggest they range from tens to hundreds of times the mass of our Sun. The reason for their large size has to do with the composition of the gas from which they formed. The gas was pristine, primordial, containing only hydrogen and helium and trace amounts of lithium. No heavier elements at all. In modern star formation, heavier elements, what astronomers call metals, even though they include things like carbon and oxygen, that aren't metals in the chemistry sense. These elements are crucial for cooling the gas. When gas cools, it can collapse more easily and fragment into smaller pieces, forming smaller stars. But the first stars had no metals to help with cooling, so the gas clouds could only cool so much before fusion ignited. This resulted in very massive stars, and massive stars are dramatic. They burn hot and bright and fast, flooding space with ultraviolet radiation. Their surfaces reach temperatures of 50,000 degrees Kelvin or more, compared to about 6,000 degrees for our Sun. They shine with the light of millions of suns, brilliant blue-white beacons in the darkness. For the first time since recombination, the universe was filled with visible light. The cosmic dark ages were ending, giving way to what's called the cosmic dawn, the epoch when the first stars ignited and began illuminating their surroundings. But these stars did more than just provide light. Their ultraviolet radiation was energetic enough to ionize hydrogen atoms, knocking electrons loose from their nuclei. Around each star, a bubble of ionized hydrogen began to grow, expanding outward as more and more atoms were hit by energetic photons. This process, called reionization, would eventually transform the universe once again. Over the next several 100 million years, as more and more stars formed, these bubbles of ionized gas expanded and merged until eventually the entire universe was reionized. The neutral hydrogen that had filled space since recombination was ionized again, and the universe became transparent in a different way, transparent to ultraviolet light and X-rays. Reionization is one of the major epochs in cosmic history, and it's still an active area of research. Astronomers use powerful telescopes to look for the most distant galaxies, trying to peer back to the era when reionization was ongoing, trying to understand exactly when and how it happened. The first stars also played another crucial role. They were the universe's first chemical factories. Remember, at this point the universe contained only the lightest elements, hydrogen, helium, and a bit of lithium. All the other elements, carbon, oxygen, nitrogen, silicon, iron, gold, everything that makes up planets and people and everything around us, those elements didn't exist yet. But inside the cores of massive stars, nuclear fusion doesn't stop with helium. As helium accumulates in the core and the hydrogen fuel runs out, the core contracts and heats up even more. At higher temperatures, helium nuclei can fuse together to form carbon and oxygen. Then, in even more massive stars, carbon can fuse to form neon and magnesium, oxygen can fuse to form silicon and sulfur, and the process continues up the periodic table. The most massive first stars would have gone through these fusion stages rapidly, in just a few million years compared to the 10 billion year lifespan of a star like our Sun. They built up cores of heavier and heavier elements, layer upon layer like an onion, with the lightest elements in the outer layers and the heaviest in the center. And then, when they ran out of fuel, when even silicon fusion in their cores couldn't generate enough pressure to hold them up against gravity, they collapsed. In a fraction of a second, the core imploded, then rebounded in the most violent explosion in the universe, a supernova. These first supernovae were extraordinary events, releasing more energy in a few seconds than our Sun will emit in its entire lifetime. They blasted the star's outer layers into space at thousands or tens of thousands of kilometers per second, enriching the surrounding gas with all the elements that had been created through fusion, plus even heavier elements created in the explosion itself. Gold, silver, platinum, uranium, all the elements heavier than iron were forged in these supernova explosions or in the collisions of neutron stars. Every gold atom in existence was created in such a cataclysmic event, either in the early universe or more recently in our galaxy's history. The supernova remnants, expanding clouds of hot gas enriched with heavy elements, mixed with the pristine hydrogen and helium around them. Future generations of stars would form from this enriched gas, and these stars would have metals in their composition from birth. They could form planetary systems, rocky worlds like Earth, because now there were elements heavier than hydrogen and helium available. The first stars, those massive population 3 stars, were seeds. They lived fast, died young, and in doing so they transformed the universe. They ended the Dark Ages, they reionized the cosmos, they enriched space with heavy elements, and they set the stage for everything that would come after. To this day, astronomers have never directly observed a population 3 star. They all died billions of years ago, and their light hasn't reached us yet. Or perhaps it's too faint and too redshifted to detect with current telescopes. But the James Webb Space Telescope, launched in 2021, is specifically designed to look for these first stars and galaxies, peering back to the cosmic dawn with unprecedented sensitivity. We may soon see them, these ancient beacons, and when we do, we'll be looking at the moment when the universe woke up, when light triumphed over darkness for the second time in cosmic history. As the first stars lived and died, as they enriched their surroundings with heavy elements and ionized the gas around them, something larger was taking shape. The universe wasn't just forming individual stars, it was forming galaxies, vast collections of millions or billions of stars bound together by gravity. We're now in the era from about 400 million to 1 billion years after the Big Bang, a period when the large-scale structure of the universe was crystallizing into the forms we recognize today. This is when the cosmic web, that magnificent three-dimensional network of filaments and voids that defines the distribution of matter on the largest scales, became clearly established. Remember those density fluctuations from inflation? Those quantum jitters stretched to cosmic sizes? They've been growing ever since, amplified by gravity. Regions that were slightly denser than average attracted more matter, becoming denser still. Regions that were slightly less dense lost matter to the denser regions, becoming emptier. Over time, this process created a foam-like structure. Matter flowed along filaments, thin strands of dark matter and gas connecting dense nodes. At the intersections of filaments, where multiple strands came together, matter accumulated most densely. These nodes became the sites of galaxy clusters and superclusters. Between the filaments were voids, vast empty regions containing very little matter. These voids could be tens or hundreds of millions of light-years across, enormous bubbles of near emptiness. And even today, most of the volume of the universe is in these voids, with matter concentrated in the filaments and nodes of the cosmic web. This large-scale structure is one of the most beautiful and profound patterns in nature. When astronomers map the positions of galaxies across billions of light-years, they see this web clearly, filaments of galaxies stretching across space, clusters where filaments meet, and vast voids in between. It looks almost biological, like neural networks in a brain or the structure of soap bubbles, and it all traces back to quantum uncertainty in the first fraction of a second after the Big Bang. The first galaxies formed in the densest nodes of this web. These early galaxies were small by modern standards, perhaps a few 100 million to a few billion times the mass of the Sun, compared to our Milky Way's roughly 1 trillion solar masses. They were also actively forming stars at prodigious rates, sometimes creating hundreds or thousands of new stars each year. These galaxies were bright, energetic, and messy. Gas was still falling into them from the surrounding cosmic web, fueling rapid star formation. Supernovae from massive stars were exploding, driving powerful winds that could blow gas out of the galaxies entirely. Black holes were forming in the centers of some galaxies, growing rapidly by consuming gas and stars, and releasing enormous amounts of energy in the process. The early universe was a violent place, at least by the standards of our relatively quiet cosmic neighborhood today. Galaxies collided and merged frequently. When two galaxies came together, their gas clouds collided, compressed, and triggered intense bursts of star formation. The resulting merged galaxy would be larger, more massive, and would eventually settle down into a more stable configuration. This process of hierarchical structure formation, where small galaxies merge to form larger ones, is a central prediction of our current cosmological models. And it's a process we can observe directly. The Hubble Space Telescope and now the James Webb Space Telescope have captured stunning images of distant galaxies in the process of merging. Their shapes distorted by gravitational interactions, streams of stars and gas connecting them. Some of these early galaxies evolved into massive elliptical galaxies, egg-shaped collections of stars with little gas and dust, their star formation largely finished. Others became disk galaxies like the Milky Way, flattened rotating systems with spiral arms where star formation continues to this day. The diversity of galaxy types and shapes we see in the modern universe has its roots in these early formation processes. How a galaxy forms, how many mergers it experiences, how much gas it retains, all of these factors shape its eventual appearance and properties. And at the centers of many of these galaxies, something remarkable was happening. Supermassive black holes were forming, objects millions or billions of times more massive than the Sun, condensed into regions smaller than our solar system. We're not entirely sure how these black holes formed so early and grew so large so quickly. They may have been the remnants of the very first stars, or they may have formed directly from collapsing gas clouds without going through a stellar phase first. What we do know is that these black holes had a profound effect on their host galaxies. As gas spiraled into a supermassive black hole, it would heat up to millions of degrees and emit intense radiation across the electromagnetic spectrum. The region immediately around the black hole, called an active galactic nucleus or AGN, could outshine the entire rest of the galaxy combined. The most luminous of these objects are called quasars, and they were especially common in the early universe. Quasars are so bright that we can see them across billions of light years, all the way back to when the universe was less than 1 billion years old. They serve as beacons, illuminating the distant universe and helping us study the conditions of the early cosmos. The energy released by active galactic nuclei could also affect star formation in the host galaxy. Strong winds and jets driven by the black hole could heat the surrounding gas, preventing it from cooling and collapsing to form stars. This is one mechanism that can shut down star formation in massive galaxies, transforming them from blue star-forming systems to red and dead elliptical galaxies. By about 1 billion years after the Big Bang, the universe had developed a recognizable structure. There were galaxies of various sizes and types, distributed along the filaments of the cosmic web. There were clusters of galaxies forming at the nodes where filaments intersected. There were supermassive black holes growing at the centers of many galaxies, and there were vast voids, nearly empty regions that made up most of the volume of space. The universe was beginning to look like home. As we move forward in time, approaching about 2 to 3 billion years after the Big Bang, we enter an era that astronomers call cosmic noon. This isn't a precise moment, but rather an extended period lasting several billion years, when the universe was at its most active, its most productive, its most dramatic. Cosmic noon, roughly spanning from 2 billion to 6 billion years after the Big Bang, was the peak epoch of star formation in the history of the universe. More stars were being born per unit time during this era than at any point before or since. It was the universe's golden age of stellar production. Why was star formation so vigorous during this time? Several factors contributed. First, galaxies were still actively accreting gas from the cosmic web, pulling in streams of fresh hydrogen and helium to fuel star formation. This gas was being channeled along the filaments of dark matter, flowing into galaxies like water running downhill. Second, galaxy mergers were still relatively common. When galaxies collided, their gas clouds would smash together, compressing the gas and triggering bursts of intense star formation. These merger-driven starbursts could produce thousands of new stars per year, compared to the 1 or 2 per year in a quiet galaxy like our Milky Way today. Third, the conditions were just right. The universe was old enough that there had been time for substantial structures to form, for gas to cool and condense, for the densest regions of the cosmic web to accumulate significant mass. But it was still young enough that there was plenty of gas available, not yet exhausted or expelled by previous generations of star formation. During cosmic noon, galaxies were brilliant and blue, their light dominated by massive young stars. These galaxies were forming what astronomers call the stellar mass function, the distribution of stars by mass that we see in galaxies today. Most of the stars in our Milky Way, including stars like our Sun, were formed during cosmic noon or shortly thereafter. This was also the era when many spiral galaxies developed their characteristic structures. As gas fell into a galaxy and began rotating, conservation of angular momentum caused it to flatten into a disk. Within this disk, density waves would propagate, regions where gas and stars were slightly compressed. These density waves triggered star formation as they passed through the gas, creating the beautiful spiral arms we see in galaxies like the Milky Way and Andromeda. Not all galaxies participated equally in cosmic noon. The most massive galaxies actually began to slow their star formation relatively early, some as early as 2 billion years after the Big Bang. This is related to what astronomers call galaxy quenching, the processes that shut down star formation in a galaxy. There are 2 main flavors of quenching. One is called mass quenching, where a galaxy simply becomes so massive that the energy from its supermassive black hole and from supernovae can heat the gas and prevent it from cooling and forming stars. The other is called environment quenching, where a galaxy falls into a dense cluster and has its gas stripped away by interactions with the hot intracluster medium or with other galaxies. These quenched galaxies, having exhausted or expelled their gas, gradually transitioned from blue to red as their massive short-lived stars died off, leaving behind longer-lived but dimmer red stars. By cosmic noon, the universe already contained a mix of actively star-forming blue galaxies and quenched red galaxies, though the blue galaxies were more numerous. Cosmic noon was also important for the build-up of heavy elements. Each generation of stars that lived and died enriched the interstellar medium with elements heavier than hydrogen and helium. By this time, about 2 billion years after the Big Bang, the metallicity of gas in galaxies had increased to perhaps 10 to 20% of the levels we see in the Sun today. This increasing metallicity had important consequences. It affected how efficiently gas could cool, which influenced star formation. It affected the properties of stars that formed, with metal-rich stars behaving differently than metal-poor stars, and crucially, it made possible the formation of rocky planets. You see, the very first stars and galaxies couldn't have had Earth-like planets, because there weren't enough heavy elements to build them from. Planets like Earth require silicon, iron, oxygen, carbon, and other elements that simply didn't exist in large quantities in the early universe. Only after several billion years of stellar processing, of stars fusing light elements into heavy ones, and supernovae scattering those elements into space, did the universe accumulate enough raw material to build rocky worlds. Our own solar system formed about 9 billion years after the Big Bang, or about 4.6 billion years ago. By that time, the cosmic metallicity had built up to the point where the gas cloud that collapsed to form the Sun contained about 2% heavy elements by mass. That 2% was enough to build the Earth, the other rocky planets, asteroids, and provide all the elements necessary for life. So in a very real sense, cosmic noon set the stage for life. Without that extended period of vigorous star formation, without billions of years of stellar alchemy converting hydrogen into heavier elements, planets like Earth couldn't exist, and neither could we. As cosmic noon gradually faded, as the universe aged past 6 or 7 billion years after the Big Bang, star formation began to decline. Galaxies were exhausting their gas supplies, or having their gas heated and expelled, or being stripped of gas through environmental processes. The inflow of fresh gas from the cosmic web was slowing. Galaxy mergers became less frequent as the expansion of space carried galaxies farther apart. The universe was entering a gentler, quieter era. Star formation would continue, of course. It continues today in galaxies throughout the universe, including our own. But never again would it reach the frenzied peak of cosmic noon, that golden age when the universe was most alive with the light of newly forming stars. Let's jump forward now to more recent cosmic history, to a time about 9 billion years after the Big Bang, or about 5 billion years ago in Earth time. The universe had settled into a mature state. Galaxies were well formed. The star formation rate had declined from its peak, but was still ongoing. The large-scale structure was fully established. For decades, cosmologists had been working to understand the expansion of the universe, trying to measure how fast it was expanding and whether that expansion was slowing down. The assumption was that it must be slowing down. After all, gravity's always attractive, always pulling everything together. The expansion should be decelerating, coasting gradually to a slower and slower rate, perhaps eventually stopping or even reversing in a big crunch. The question was how much the expansion was slowing. Was it enough to eventually halt and reverse, leading to collapse? Or would the universe expand forever, but at an ever-decreasing rate? This depended on the density of matter in the universe compared to a critical value. If the density was above critical, collapse. Below critical, eternal expansion but decelerating. Right at critical, the universe would asymptotically approach zero expansion rate. To answer this question, astronomers needed to measure how the expansion rate had changed over time, and to do that, they needed something they could use as a standard candle, an object whose intrinsic brightness was known so that by measuring its apparent brightness, they could calculate its distance. The tool they chose was a type of supernova called type Ia. These supernovae occur when a white dwarf star, the dense remnant left behind when a sun-like star dies, accumulates matter from a companion star until it reaches a critical mass. At that point, carbon fusion ignites throughout the white dwarf almost simultaneously, and the star explodes completely, leaving no remnant behind. Because Type Ia supernovae always explode at the same critical mass, they always release roughly the same amount of energy, making them incredibly reliable standard candles. By measuring how bright a Type Ia supernova appears and comparing that to its known intrinsic brightness, astronomers can calculate how far away it is. And by measuring the redshift of the supernova's host galaxy, they can determine how much the universe has expanded since the light was emitted. In the 1990s, two independent teams of astronomers began a systematic survey of distant Type Ia supernovae, looking for these cosmic mile markers stretching back billions of years into the past. They expected to measure the deceleration of the expansion and determine the fate of the universe. What they found shocked the world. In 1998, both teams, the Supernova Cosmology project led by Saul Perlmutter and the High Z Supernova Search team led by Brian Schmidt and Adam Rees, announced their results. The distant supernova were fainter than expected, significantly fainter. This could mean only one thing. The universe was expanding faster now than it had been in the past. The expansion wasn't slowing down, it was speeding up. This was completely unexpected. It violated everything cosmologists thought they knew about the universe. Acceleration requires something pushing galaxies apart, something with a repulsive effect, something that acts opposite to gravity. But what could that possibly be? The answer, it turns out, had been hiding in Einstein's equations all along. When Einstein first developed his theory of general relativity, he realized that his equations allowed for a term called the cosmological constant, represented by the Greek letter lambda. This term acts like a property of space itself, an energy density inherent to the vacuum that creates a kind of anti-gravity, pushing space apart rather than pulling it together. Einstein actually added this term to his equations initially to create a static universe, because at the time it was believed the universe was eternal and unchanging. When Hubble discovered that the universe was expanding, Einstein called the cosmological constant his biggest blunder. But now, 80 years later, it seemed the cosmological constant was making a comeback. The simplest explanation for the observed acceleration is that the universe is filled with dark energy, a form of energy associated with empty space itself, unlike matter or radiation, which dilute as the universe expands. Dark energy maintains a constant density even as space grows. This means that as the universe expands and matter becomes more spread out and less dense, dark energy becomes increasingly dominant. In the early universe, when matter was dense, gravity won. It slowed the expansion. But as the universe expanded and matter diluted, dark energy, which wasn't diluting, began to take over. Around 5 to 6 billion years ago, about the time the solar system was forming, dark energy became dominant. From that point forward, the expansion of the universe has been accelerating. The discovery of cosmic acceleration earned Perlmutter, Schmidt and Rees the Nobel Prize in Physics in 2011. It was one of the most important cosmological discoveries of the past century, fundamentally changing our understanding of the universe's composition and fate. Because when we account for dark energy, when we measure all the different components of the universe, we find something startling. Ordinary matter, the stuff that makes up stars and planets and us, constitutes only about 5% of the total energy density of the universe. Dark matter, which we can detect through its gravitational effects but don't understand, makes up about 27%, and dark energy makes up the remaining 68%. More than 2/3 of the universe consists of this mysterious energy that we don't understand, that pushes space apart, that is driving an accelerating expansion that will shape the ultimate fate of the cosmos. What is dark energy? We honestly don't know. The cosmological constant is one possibility, perhaps the simplest, but it comes with its own theoretical problems, particularly the question of why it has the value it does. Other possibilities include more exotic forms of energy, sometimes called quintessence, that can vary in space and time, Understanding dark energy is one of the greatest challenges facing cosmology today. Experiments and observations are underway to measure its properties more precisely, to look for any variation in its density or effects, to search for clues that might reveal its true nature. But whatever dark energy is, its discovery has profound implications. It means the universe will expand forever, and not just forever, but at an accelerating rate. Galaxies beyond our local group are being carried away from us ever faster, and eventually, trillions of years from now, they will recede so quickly that their light can never reach us. The observable universe will shrink, until distant observers in the far future will see only their own local group of gravitationally bound galaxies, surrounded by darkness in all directions. But that's looking very far ahead. For now, we live in a universe that's still full of galaxies, still forming stars, still evolving and changing. The discovery of dark energy hasn't changed the present. It's changed how we think about the future, and it's reminded us that the universe still holds profound mysteries, even after 14 billion years of evolution and a century of modern cosmology. We've now arrived at the present day, or rather, at the recent cosmic past. The light we see from distant galaxies is ancient, showing us the universe as it was millions or billions of years ago. But let's consider the universe as it exists now, approximately 13.8 billion years after the Big Bang. The universe today is vast beyond comprehension. The observable universe, the region from which light has had time to reach us since the Big Bang, extends about 46 billion light-years in all directions. That's not a mistake or a violation of the speed of light. While light has been travelling for 13.8 billion years, the universe has been expanding all that time, so the objects that emitted that light are now much farther away than 13.8 billion light-years. Within this observable universe there are approximately 2 trillion galaxies, each containing millions, billions, or even trillions of stars. The total number of stars in the observable universe is estimated at around 1 billion trillion, or 10 to the power of 24. That's more stars than all the grains of sand on all the beaches on Earth, though that comparison has become something of a cliché because it's used so often. Our Milky Way galaxy is a fairly typical large spiral galaxy, containing somewhere between 100 billion and 400 billion stars, depending on how you count. It's about 100,000 light-years across, with our solar system located about 26,000 light-years from the galactic centre, about halfway out in one of the spiral arms. The Milky Way is part of the local group, a collection of about 80 galaxies bound together by gravity. The local group spans about 10 million light-years and includes the Andromeda Galaxy, another large spiral about 2.5 million light-years away, the Triangulum Galaxy, and numerous smaller dwarf galaxies. The local group itself is part of the Virgo supercluster, an enormous structure about 110 million light-years across containing tens of thousands of galaxies. And even the Virgo supercluster is just one lobe of an even larger structure called Laniakea, which contains about 100,000 galaxies spread across 520 million light-years. These nested structures, each larger than the last, trace the pattern of the cosmic web that formed in the first few 100 million years after the Big Bang. Matter flows along filaments, accumulates at nodes, and leaves vast voids in between. It's a pattern written by gravity, sculpted by dark matter, and illuminated by the light of 1 billion trillion stars. The universe continues to evolve. Stars are still being born, though at a slower rate than during cosmic noon. In our Milky Way, about 1 or 2 new stars form each year. Some of these are massive stars that will live fast and die young in supernova explosions. Others are sun-like stars that will burn steadily for billions of years. And still others are small red dwarfs that will outlive every other type of star, burning their hydrogen fuel so slowly that they'll continue shining for trillions of years. Planets are forming too. Observations from telescopes like Kepler and TESS have revealed that planets are incredibly common. Most stars appear to have at least one planet, and many have multiple planets. The galaxy likely contains hundreds of billions of planets, and a significant fraction of these may be rocky worlds orbiting in the habitable zones of their stars, where liquid water could exist on the surface. Whether any of these planets harbour life, we don't yet know. Earth's life arose remarkably quickly after our planet cooled enough to have liquid water, which suggests that life might be common in the universe. But we've only detected life in one place so far, here on Earth, which could mean it's incredibly rare. This is one of the great open questions of our time, and projects like SETI continue to search for signals from potential alien civilizations. Black holes continue to grow in the centres of galaxies, some through the steady accretion of gas and stars, others through dramatic mergers when galaxies collide. The Laser Interferometer, Gravitational Wave Observatory or LIGO, has detected dozens of black hole mergers in recent years, listening to the ripples in space-time created when these cosmic monsters spiral together and merge, and galaxies themselves continue to interact and merge. In fact, the Milky Way and Andromeda are on a collision course, destined to merge in about 4.5 billion years. When they do, they'll create a larger elliptical galaxy that astronomers have already nicknamed Milkomeda. Our solar system will likely survive this collision intact, though we'll be flung into a different orbit within the merged galaxy. The night sky will look very different, with the combined stars of two galaxies spread across the heavens. The universe is also becoming increasingly dark. Star formation has been declining for billions of years and will continue to decline. Eventually, in the far future, all the gas in galaxies will either be used up to form stars or ejected or stripped away. Star formation will cease. The last stars will be born, live, and die, and no new ones will replace them. This process will take trillions of years, far longer than the current age of the universe. But it's inevitable. The stelliferous era, the age of stars, is only a temporary phase in the universe's history. Before it, there was darkness. After it, there will be darkness again. As the small stars die out, the universe will be populated by cooling white dwarfs, neutron stars, and black holes. These remnants will slowly cool, radiating away their energy over incomprehensible timescales. Eventually, even black holes will evaporate through a process called Hawking radiation, though this takes so long that a solar mass black hole would require 10 to the 67 years to completely evaporate. In the far, far future, perhaps 10 to the 100 years from now, the universe will reach a state called heat death. All temperature differences will have equalized. No more energy can be extracted to do work. Stars will be long gone, black holes will have evaporated, and only a thin soup of photons and fundamental particles will remain, spread across an ever-expanding space that has grown so large that the average density approaches zero. This is the ultimate fate predicted by our current understanding of physics, assuming dark energy continues to drive acceleration as it does now. It's a cold, quiet ending, but it's also so far in the future that it's hard to wrap our minds around. We're talking about timescales trillions of times longer than the current age of the universe. But let's not get too melancholy about the far future. We live in the age of stars in a universe full of light and structure and complexity. We live on a planet that has liquid water, an atmosphere, and life. We live in a galaxy that's still forming new stars, still dynamic and active. We live in an era when we can look up at the night sky and see thousands of other galaxies with our telescopes, trace the history of the universe from the Big Bang to today, and ask questions about where we came from and where we're going. And that brings us to perhaps the most profound aspect of the Big Bang story. We are part of it. Every atom in our bodies was forged in the Big Bang or in the core of a star. The hydrogen in our water molecules formed in the first 3 minutes of cosmic history. The carbon in our cells, the calcium in our bones, the iron in our blood, all of it was created in stellar furnaces and scattered across space in supernova explosions. We are quite literally made of stars. We're a way for the universe to know itself, to study itself, to understand its own history. When you look up at the night sky and contemplate the vastness of space and time, you are the universe looking back at itself with wonder. There's something deeply moving about that realization. We often think of ourselves as separate from nature, from the cosmos, as observers peering in from the outside. But we're not outside. We're inside. We're part of the story. part of the grand narrative that began 13.8 billion years ago with the Big Bang and continues today with every breath we take, every thought we think. The elements that make us possible required billions of years of stellar alchemy. The planets we live on required heavy elements that only became abundant after many generations of stars lived and died. The stable conditions that allow life to flourish required a universe old enough and cool enough and structured enough that stable solar systems could form and persist for billions of years. In a very real sense, the universe had to be at least several billion years old before anything like us could exist. And the universe will continue for trillions upon trillions of years after we're gone. We exist in a narrow window of cosmic history, in the brief age of stars, when the universe is neither too young nor too old to support complex structures like galaxies and solar systems and life. That's a remarkable piece of good fortune, if we can call it that. Or perhaps it's not fortune at all, but necessity. In a multiverse of infinite possibilities, if such a thing exists, we find ourselves in a universe capable of producing us simply because we couldn't exist in any other kind. This is the essence of the anthropic principle, the idea that the universe's properties must be compatible with the existence of observers like us, because otherwise we wouldn't be here to observe them. Whether you find this philosophical argument satisfying or frustrating, it points to a deep connection between the laws of physics, the history of the cosmos, and our own existence. We are not accidental. We are not separate. We are embedded in the cosmic story as thoroughly as a wave is embedded in the ocean. Before we conclude our journey, it's worth reflecting on how we know all of this. How can we possibly claim to understand what happened in the first microsecond after the Big Bang, or what the universe was like billions of years ago? We weren't there. We can't go back in time. We can't run the Big Bang again in a laboratory to test our theories. And yet we can make these claims with confidence because the universe itself preserves evidence of its history. The cosmos is like a vast archaeological site, with clues scattered across space and time, waiting to be discovered and interpreted by patient observers. The most direct evidence comes from looking at distant objects. When we look at a galaxy 1 billion light-years away, we're seeing it as it was 1 billion years ago, because that's how long its light took to reach us. The more distant an object, the farther back in time we're seeing. The most distant galaxies observed by the James Webb Space Telescope are seen as they were just a few 100 million years after the Big Bang, showing us the universe in its youth. By studying galaxies at different distances, and thus at different epochs, astronomers can piece together the history of galaxy formation and evolution. They can see how galaxies change over time, how their star formation rates vary, how their structures evolve. It's like looking at photographs of a person at different ages and using those to understand human development. The cosmic microwave background is another crucial tool. As we discussed earlier, this radiation was released when the universe became transparent, about 380,000 years after the Big Bang. It carries information about the conditions at that time, encoded in tiny temperature variations across the sky. By mapping these variations with satellites like Planck, scientists can learn about the density of matter, the geometry of space, the amount of dark matter and dark energy, and many other cosmic parameters. The CMB is like a baby picture of the universe, showing us what it looked like in its infancy. And just as you might be able to predict some features of an adult's appearance from their baby pictures, cosmologists can use the CMB to predict what the universe should look like today, and those predictions match observations remarkably well. Then there's Big Bang nucleosynthesis, which we covered earlier. The abundances of light elements like hydrogen, helium and lithium observed in the oldest stars and gas clouds match the predictions from Big Bang theory with stunning precision. This is evidence from the first 20 minutes of cosmic history, preserved in the composition of matter throughout the universe. Gravitational waves provide yet another window into cosmic history. When massive objects like black holes or neutron stars orbit each other and merge, they create ripples in space-time that propagate outward at the speed of light. LIGO and other gravitational wave observatories detect these ripples, allowing us to study cosmic events that don't emit light. Future space-based gravitational wave detectors might even be able to detect ripples from the inflationary epoch, providing direct evidence of what happened in the first fraction of a second after the Big Bang. Particle accelerators like the Large Hadron Collider recreate the conditions of the early universe by smashing particles together at enormous energies. By studying what happens in these collisions, physicists can understand the behavior of matter and energy under extreme conditions, testing theories about the quark-gluon plasma, the electroweak force, and other aspects of the early universe. And of course, there's the theoretical framework that ties all of this together. Einstein's general relativity describes how gravity works and how space and time are related. Quantum mechanics describes the behavior of matter and energy at small scales. The Standard Model of particle physics describes the fundamental particles and forces. When these theories are combined with observations, they paint a consistent, coherent picture of cosmic history from the Big Bang to today. This doesn't mean we know everything or understand everything. Far from it. Dark matter and dark energy remain mysterious. We don't have a complete theory of quantum gravity. We don't fully understand how the first stars and galaxies formed, or how supermassive black holes grew so large so quickly, or whether inflation really happened, and if so, exactly how. But the remarkable thing is how much we do know, how many independent lines of evidence all point to the same story, how observations separated by vast distances and enormous spans of time all fit together into a coherent narrative. The Big Bang theory isn't just speculation or guesswork. It's one of the most well-tested, well-supported theories in all of science. And it's a theory that has profound implications. It tells us that the universe had a beginning, that it has been evolving and changing for billions of years, that it will continue to evolve far into the future. It tells us where matter came from, where stars came from, where galaxies came from, where we came from. It connects the smaller scales of quantum mechanics to the larger scales of cosmic structure. It links the first fraction of a second after the Big Bang to the night sky we see today. It provides a framework for understanding not just what the universe is like, but why it's like that, how it got to be this way through billions of years of physics playing out across billions of light-years of space. The Big Bang theory is humanity's origin story, written in mathematics and confirmed by observation. It's a story of emergence, of complexity arising from simplicity, of structure forming from chaos, of order appearing where there was once only uniform energy. And it's a story that isn't finished. We're still learning, still discovering, still refining our understanding. New telescopes are revealing distant galaxies we've never seen before. New experiments are probing the nature of dark matter and dark energy. New theoretical work is exploring the connection between quantum mechanics and gravity, searching for a unified theory that can describe the Planck epoch. Every answer raises new questions. Every discovery reveals new mysteries. And that's exactly as it should be. Science isn't about having all the answers. It's about asking better and better questions, pushing the boundaries of knowledge, standing at the edge of the unknown and taking one more step forward. We've travelled a long way together tonight, from the incomprehensible instant of the Planck epoch to the vast, expanding universe of today, from temperatures beyond imagination to the cool darkness of interstellar space, from a universe containing nothing but energy to one filled with galaxies and stars and planets, and, on at least one of those planets, life and consciousness. It's been a journey of 13.8 billion years, compressed into a single evening. And if you're still with me, still awake, still listening, I hope you found something in this story that resonates with you. Maybe it's the sheer scale of it all. The realization of how vast and old and intricate the universe truly is. Maybe it's the connections, the way everything links together, from quantum fluctuations to galaxy clusters, from quarks to consciousness. Or maybe it's something more personal, more immediate. The knowledge that you are made of stardust, that the atoms in your body have been on an incredible journey, forged in the hearts of stars scattered across space, eventually gathering on this planet to become part of you. You are ancient and you are new. You are a temporary arrangement of matter that will someday dissolve back into the universe from which it came. But while you exist, while you breathe and think and wonder, you are the universe experiencing itself. There's a quote often attributed to Carl Sagan, though he was paraphrasing others who came before him. He said, "We are a way for the cosmos to know itself." And it's true. Consciousness, awareness, the ability to ask questions and seek answers, these are among the most remarkable phenomena in the universe. As far as we know, they're rare, perhaps even unique to life on Earth, though we suspect life might exist elsewhere. But whether common or rare, consciousness is profound. It allows the universe to reflect on its own existence, to study its own history, to contemplate its own future. Without observers, without minds to perceive and understand, would the universe even exist in any meaningful sense? That's a philosophical question without a clear answer, but it's worth pondering. The Big Bang Theory tells us that we live in a universe that had a beginning, that has been evolving ever since, and that will continue evolving long after we're gone. It tells us that we're part of something much larger than ourselves, a cosmic story that spans billions of years and billions of light years. And yet it also tells us that we're connected to all of it, that we're made from the same material as stars, that we're governed by the same laws of physics that shaped galaxies. In a universe that can sometimes feel cold and indifferent, there's something comforting about that connection. We're not separate from nature. We're not aliens in a strange land. We're home. This universe is our universe. These atoms are our atoms. This story is our story. And what a story it is. It begins with a moment of unimaginable energy, a singularity beyond comprehension. It moves through epochs of transformation, each one setting the stage for the next. Forces separate. Particles form, nuclei fuse. Atoms assemble. Stars ignite. Galaxies gather. Planets coalesce. And eventually somewhere, somewhen, life emerges, and with it the capacity to look back across all those billions of years and understand how we got here. The universe didn't have to be this way. The laws of physics could have been different. The constants of nature could have had other values. With even slight changes, stars might not form, or they might burn out too quickly for planets to develop, or atoms might not be stable, or chemistry might not be rich enough to support complexity. But the universe is the way it is, and we are here to witness it. Whether that's luck, necessity, or something else entirely, it's a gift. Every sunrise, every starry night, every breath of air, every heartbeat is part of this ongoing story that began with the Big Bang and continues in us, through us, because of us. As you drift towards sleep tonight, if you haven't already, I invite you to hold this story gently in your mind. The universe began in fire and will likely end in ice. But between those extremes, there's this incredible period, billions of years long, where stars shine and galaxies spiral and life exists and asks questions about where it came from. You are part of that interval. You are part of that questioning. You are stardust that learned to think, atoms that learned to contemplate atoms, the universe awakening to itself. And tomorrow when you wake, the universe will still be here, still expanding, still evolving, still holding mysteries we haven't solved and wonders we haven't discovered. The journey of the cosmos continues, and you're invited along for the ride. The story of the Big Bang is in many ways the story of everything. It's the story of space and time, of matter and energy, of forces and fields and all the intricate patterns they create. It's a story told in mathematics and confirmed by observation, a story that began nearly 14 billion years ago and continues in this very moment. We've explored together the first impossible instant, when all the rules we know broke down and the universe existed in a state beyond our ability to describe. We've witnessed cosmic inflation, that brief but dramatic expansion that set the stage for everything to come. We've watched as quarks condensed from plasma, as nuclei formed from protons and neutrons, as atoms assembled from nuclei and electrons. We've stood at the threshold of the cosmic dark ages, that long period of waiting when the universe was dark and formless, preparing for the light to come. We've seen the first stars ignite, those massive brilliant beacons that ended the darkness and began the long process of enriching space with heavy elements. We've watched galaxies emerge from the cosmic web, growing through mergers and accretion, forming stars at prodigious rates during cosmic noon, then gradually quieting as their gas supplies dwindled. We've discovered the acceleration of expansion, that surprising revelation that dark energy dominates the universe and drives it toward an ever faster expansion. And we've arrived at today, at a universe that's mature but still active, still full of stars and galaxies, still evolving, still holding secrets waiting to be uncovered. Throughout this journey, one theme has emerged again and again. Connection. Everything in the universe is connected to everything else. The quantum fluctuations of the first instant are connected to the distribution of galaxies today. The first stars are connected to the planets that would form billions of years later. The fusion reactions in stellar cores are connected to the atoms in your body. You are not separate from this story. You are part of it, woven into the fabric of cosmic history as intimately as a single thread is woven into a blanket. Your very existence depended on billions of years of cosmic evolution, on the precise values of physical constants, on the formation and death of countless stars, on the condensation of a particular cloud of gas and dust into a solar system about 4.5 billion years ago. And here you are, the product of that long chain of events, a conscious entity capable of understanding the story of which you're a part. That's extraordinary. It's miraculous even, though the miracle is explained not by magic, but by physics and chemistry and biology, by natural processes playing out over vast stretches of time. If you've drifted off to sleep during this journey, that's perfectly okay. In fact, it's expected. These quiet explorations are meant to be soothing, meant to accompany you into that gentle twilight between waking and sleeping where thoughts become dreams and the boundaries between self and universe blur just a little. And if you're still awake, still listening, I hope you found something worthwhile in this telling of the cosmic story. Maybe you'll dream of galaxies tonight, of stars being born in clouds of gas, of light travelling across billions of years to reach your eyes. Maybe you'll dream of the Big Bang itself, that moment of creation when everything began. Or maybe you'll just sleep peacefully, your mind at rest, your body relaxed, your place in the universe secure. Because you do have a place here. You belong here. You're made of star stuff, as Carl Sagan said, and you are the universe experiencing itself, as the philosopher Alan Watts observed. You are both infinitesimally small and infinitely important, a tiny speck in the vastness of space, and yet a miracle of complexity and consciousness. The universe is vast beyond measure, it's old beyond comprehension, it's strange and beautiful and terrifying and wonderful, and you get to be part of it, for this brief moment in cosmic time, for these few decades of awareness between the darkness that came before and the darkness that will come after. Make the most of that time. Look up at the stars. Wonder about distant galaxies. Ask questions about where we came from and where we're going. Read about science and astronomy and cosmology. Watch videos like this one if they help you feel connected to something larger than yourself. Because we need that connection. In a world that can feel isolating and overwhelming, it helps to remember that we're part of something vast and ancient and ongoing. The same forces that shaped galaxies are at work in your body, in the chemical reactions that keep you alive, in the electrical signals that create your thoughts. The same atoms that were forged in the Big Bang and in stellar cores are now arranged in patterns that allow you to read these words and understand their meaning. That's the real miracle of the Big Bang story. Not just that the universe began, but that it began in such a way that 13.8 billion years later, parts of it could become conscious, could look back across all that time and understand how they came to be. You are the universe waking up. You are the cosmos becoming aware of itself. And that's something worth celebrating, even as you drift off to sleep, even as the day releases its hold and night takes over, even as consciousness fades and dreams begin. Thank you for joining me on this journey tonight. Thank you for listening to this long, winding story of everything, from the first moment to the present day. Thank you for your patience, for your curiosity, for your willingness to contemplate the vast and the ancient and the strange. If you enjoyed this exploration, If you found something valuable in this telling of the cosmic story, a like would be deeply appreciated. It helps this small channel continue creating these quiet journeys through space and time. And if you'd like to hear more, if you'd like to explore other cosmic mysteries and astronomical wonders, please consider subscribing. Knowing you're out there, listening, wondering, asking questions alongside me makes every video worthwhile. To those of you already subscribed, thank you. Truly, thank you. Your support means more than you might realize. You're part of a community of curious minds, of people who look up at the night sky and feel that sense of wonder, that desire to understand our place in the cosmos.